Okay, so today now we're going to begin to actually talk about this idea of differentiation. Okay, and differentiation is the name of the process that we use to find the gradient function of a curve. So we know that over a curve, along a curve I should say, the gradient is different at every point. Well, not every point, but the gradient's changing. Okay, it goes from positive to negative, it goes from steep to less steep, all sorts of things. Okay. So what we can do is we can come up with a function or an equation that describes what's happening with the gradient. Okay, so let's say, that's our original function. We can come up with another function that describes what's happening with the gradient. So at this point, clearly the gradient is 0, so our gradient function would be equal to 0. At this point here, the gradient's also 0. We have negative gradient between there. Okay, we then have positive gradient after that and positive gradient after that. So maybe my gradient function would look something like the blue graph. So the whole point of differentiation is to come up with a way to find this blue gradient function. And once we've got the gradient function, then we can calculate the gradient of the orange curve at any point by substituting that x coordinate into the blue curve. Okay, so that's the aim of differentiation. Over the last couple of videos, you've looked at ideas around rates of change. We've looked in particular at this idea of instantaneous rate of change, which is all about what we're interested in now. How can we find the gradient of a curve at a given point? Okay. So the process that we use to obtain the gradient of a function at any point x is called differentiation. Okay. We differentiate to find the gradient function. And one of the fundamental things about that is that we need to understand that the gradient of a curve at any given point is equal to the gradient of the tangent at that point, and that's fundamental. We're going to need to make use of our limits, which we've looked at over the last two videos, as we're calculating the gradient function. Okay, so let's have a look at this diagram. We'll just talk this diagram through in a static sense, and then I'm going to flip over to a file I've got set up in the CAS program to sort of see it in a slightly more dynamic way. I'm also going to use a few different letters in the dynamic program. I just have to change a couple of things. Okay, so what we have here is a curve, y equals f of x. So that's in green. And we're going to draw, we're interested in finding, what we're ultimately interested in finding is the gradient of the curve at this point m. Okay, so that means we need to be able to find the gradient of the tangent at this point m. Those two things would be the same. Those two things would be the same. Okay, so we've drawn in. So we've got m is a point on the curve. It has coordinates of x, f of x. So its x coordinate is just some generic value x. Therefore, its y coordinate is f of x, subbing x into the rule. Okay. A tangent is drawn at m. So that means it has the same gradient as the green curve at m. We want to let n be the point on the curve with coordinates x plus h, f of x plus h. So n is another point on the curve, okay? And it's just h away from here, okay? So its x coordinate is x plus h, which means that its y coordinate is f of x plus h, okay? All right, so we've just got 2 points on the curve. So we can join those 2 points with a secant. I think we've met the word secant in a previous video. It's just a straight line that joins 2 points on a curve. Okay, and we can obviously calculate the gradient of that secant because it's just a straight line. Okay, so it's just rise over run. Yeah, so rise over run. So the rise would clearly be f of x plus h minus f of x, so the difference in the y values. And the run is clearly x plus h minus x, so that's just going to be h. Okay? Obviously this distance here is h. So therefore the gradient is going to be the rise, which is, so the gradient of the secant mn is going to be the rise, which is f of x plus h, minus f of x all over the run, which is h. Okay, so our purpose now is to find the gradient of the tangent using the gradient of the secant. Okay, so what we want to think about here is, how do I use, now that we've come up with a way to describe the gradient of this blue line, how do I use that to find the gradient of the red line? And this is all to do with limits. I'm going to go over to the dynamic version now, and then we'll come back here. So here I've got the same thing. I've had to use the letter A in place of X. Okay, so we're trying to approximate the tangent at a point M with an x-coordinate of a rather than x-coordinate of x, but otherwise everything else is the same. Okay, so what we've got here now is we're actually working with some numbers. I've put a specific function in here. So what the CAS is calculating for us is the gradient of the chord, or the secant, that should be mn. Okay, so the gradient of the blue line is being calculated and it's currently 2.8, and the gradient of the tangent at m is 1.41. Okay, so what we want to think about is how can we get the gradient of the blue line to be equal to the gradient of the red line. Okay, and that's going to happen. Obviously, we're going to be able to improve our estimate. So the blue line's currently not a very good estimate for the gradient of the red line. But if we move in closer to m, it becomes a better and better estimate. And we saw that in the previous exercise when we were looking at rates of change. One of the methods we used to approximate the gradient of a curve at a point was to take 2 points that were very close together and calculate the gradient of the straight line that joins them. And that gave us a good approximation for the gradient of the tangent, and hence the gradient of the curve. So here we see as we move the 2 points closer and closer together, the gradient of the blue line is approaching the gradient of the red line. And this is where this idea of limits comes in. Okay, so what we want to think about is what are we actually changing by moving n closer to m? And the easiest way to talk about it is what we're doing is we're making h small. So see, remember h is that horizontal distance. Look at it along the x-axis there. As we move n closer and closer and closer to m, what's happening is h is getting closer and closer and closer to 0. Okay, so we want to think about the fact that the gradient of the blue line will be equal to the gradient of the red line, the tangent, will be equal to the gradient of the blue line as we look at what happens as h approaches 0. We take the limit as h approaches 0 of the gradient of the blue line, and we'll get the gradient of the red line. Okay, so that's the whole idea about derivative. Okay, let's go back over to our notes, and that's written out here. So our purpose now is to find the gradient of the tangent at m by using the secant mn, and we'll do this by making h small. That is by taking the limit as h approaches 0. So this will mean as we make h small, x plus h gets closer and closer to x, therefore n gets closer and closer to m along the curve, and therefore the gradient of the secant gets closer and closer and closer to the gradient of the tangent. Hence the limiting value will be equal to the gradient of the tangent. Okay, so in summary, what we essentially want to be able to do then is say that the gradient of the tangent is equal to the limit as h approaches 0 of the gradient of the secant. Okay, and that the gradient of the tangent at m, okay, is equal to the gradient of f of x at m. And so we now have a way to calculate the gradient of the curve at a particular point with an x-coordinate of x. Okay, so let's talk a bit about notation, and let's bring that together. So the gradient of a curve y equals f of x at any value x can be denoted in a couple of different ways. The neatest way is to call it f dash x. Okay, the derivative of y with respect to x, if x is the variable in our function, would be called dy dx. I'll talk more about this notation as we go on. Okay, we can also write it as the derivative with respect to x. We're differentiating, and our function is in terms of x, so we're differentiating in terms of x of f of x. So all three of these things are ways of calculating the derivative of y equals f of x. This would be if your functions if function notation is used, it would definitely call it the derivative f dash x or g dash x or h dash x. But if there's no function notation, then you'll be forced to use this Leibniz notation, so dy dx or d dx. This is called the derivative of the function f. Okay, so f dash x is the derivative of f. Okay, and to find the derivative, we use the process of differentiation. The derivative can also be referred to as the gradient function because it describes the gradient of the curve at any point x. And as I said, the process of finding the derivative or the gradient function is called differentiation. Okay, so here we now have our derivative of f of x is called f dash x, and we calculate it in this way. Okay, as I said to you when we were doing limits the other day, I'd like us to get in the habit of including brackets here to get the sense that the limit is an operation that we're going to be doing to this. We can't just divide by the limit or move it onto the other side or those sorts of things. Okay, so it is f dash x, the derivative of f, is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. As we know, the derivative gives the gradient of the curve y equals f of x at any point x, and it's also referred to as the gradient function. When we use this particular formula to find the gradient function or the derivative, it's called differentiation by first principles. And what we'll look at over the next few videos is how we can come up with rules to differentiate particular kinds of functions that mean that we don't have to do this process every time. But it is important that you understand this process, that you can execute this process, and that you know how to use it. Okay, so it is important to do this, and we're going to focus on this process, differentiating by first principles, for this lesson. Before next week we'll go into looking at how we can shortcut this process. Okay, let's use first principles to differentiate f of x equals x squared, and hence find the gradient of f of x when at the point, let's get rid of when, at the point 416. Okay, so we want to calculate this, our derivative by first principles. Okay, so we know that f dash x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay, so we know what f of x is, so that's nice and easy, that's going to go there. We need to know what f of x plus h is. Now I'm going to do that off to the side just to give me some space to do my sort of expanding. So f of x plus h, actually let me write them both out here. So we know that f of x is x squared, we therefore know that f of x plus h is equal to x plus h all squared, and I'm going to expand that out before I substitute it in. So it's going to be x squared plus 2hx, or xh, doesn't matter, plus h squared. Okay, so now let's put this information in. So f of x is that, f of x plus h is that. So we haven't taken the limit yet, so we can't get rid of that. We're still taking the limit as h approaches 0 of f of x plus h, which is x squared plus 2hx plus h squared, minus f of x, which is x squared, and we've got all of that over h. Okay, so now let's focus on simplifying this expression, because we know from our work with limits in the previous lesson, we can't just substitute h equals 0 into this expression yet, because then we would be dividing by 0. So we have to see what we can do to manipulate and simplify this so that we can then take the limit. So again, we haven't taken the limit yet, so it's still equal to the limit as h approaches 0. Now on the numerator, x squareds are going to cancel out. You've got x squared minus x squared. Okay, and then we have 2hx plus h squared all divided by h. So we've got a nice common factor of h there. So if we think about on the numerator, h would come out as a common factor. We get h times 2x plus h squared over h. And so the h's are going to cancel out. And now we've fixed the problem where we had an h in the denominator, which was preventing us from taking the limit. So now we have an expression that we can take the limit as h approaches 0, so we can essentially substitute h equals 0 in here, and we're going to get 2x plus 0 squared, so 2x. Okay, so therefore the derivative function, okay, the derivative is 2x. The gradient function is 2x. Now, if we want to know the gradient at this point, okay, that is when x equals 4 and y equals 16, the 16 is completely irrelevant to doing that. There's no y in this function at all. This isn't y anymore. This is the derivative of y, the rate of change, the gradient. This relationship connects x and gradient, okay? So therefore the only thing we can sub in here, the y is useless to us. We didn't need to be given it, but it's there just to make sure that you understand what needs to be substituted in. We're going to be substituting 4 into the function. So if we want to know the gradient when x equals 4, we can write f dash at 4. Okay, So we are working at gradient when x is 4. And then we just sub that into our gradient function. So it's just going to be 2 times 4, and so therefore the gradient is 8. So at the point 416, the gradient is 8. So again, let's think about what we've got here. It was a basic parabola, y equals f of x. Okay. At this point here, 416, what we're seeing is the gradient of the curve, the gradient of the tangent is 8. Okay. All right, let's have a go at another one. Use the method of first principles to find f dash at -1 if f of x is this. Okay, so this requires us to find the derivative of f and then substitute x equals -1 into it. Okay, so f dash at x, you can actually do it straight away with the -1, but I think it's better, it helps you to understand what's happening a bit better if you always calculate the derivative first and then substitute the value in. Okay, so we know f dash at x, derivative by first principles, it's the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. Again, let's work out our expression. So we know f of x is x squared plus 3x, and therefore f of x plus h is x plus h squared plus 3 times x plus h. Let's expand and tidy up here. So this is x squared plus 2hx plus h squared, and then we've got plus 3x plus 3h. Okay, I'm not going to bother tidying that up any more than that. I'm just going to write that straight in. Okay, so once again, we have this is f, that's going to go in there, and we have this is f of x plus h, that's going to go in there. Okay, so we're going to have the limit as h approaches 0 of x cubed plus 2hx plus h squared plus 3x plus 3h. Okay, and then we're going to subtract f of x, which is, let me just move that over a bit, got a bit crowded here, and we're going to subtract f of x, which is x squared plus 3x. Now be really careful here because we're subtracting all of f of x, so you must make sure that's in a bracket because you need to subtract both x squared and 3x. Okay, so that means we're calculating the limit as h approaches 0. Oh, sorry, that cube didn't move along when I moved. Okay, so what we see here, a couple of things will cancel. We're going to have x cubed minus x cubed. We're also going to have plus 3x minus 3x. Alright, so this happens every time when you do derivative by first principles. The terms that have nothing to do with h all cancel out when you do the subtraction. And then what that means is every term that remains has h as a common factor. So that's why you're always going to be able to find the limit, because you can take h out and you'll have 2x plus h plus 3. And that means then we can divide by h and cancel out the denominator. Okay, so we're going to get limit as h approaches 0 of 2x plus h plus 3. And so now, taking the limit as h approaches 0, we essentially sub h equals 0 in. And so we're just going to get, now that we're taking the limit, 2x plus 0 plus 3. So the derivative of this function is 2x plus 3. The gradient function is 2x plus 3. So therefore, if we want f dash at -1, we want 2 times -1 plus 3, which is minus 2 plus 3, which is 1. Okay, so the gradient of this curve when x equals -1 is 1. Okay, again, thinking about that, you've got, it's a parabola with x-intercepts at -3 and 0, and it's happy. We've just found when x equals -1, which will be about there. Doesn't matter what the y value is, but we've found at this point the gradient is equal to 1. So the gradient of the curve at that point will be 1. Okay, so I'd like you to work through some derivatives by first principles, practicing that algebra, that process of taking a limit, also then potentially using your derivative in context of finding a gradient. The worksheet is available to you on Canvas.